Hello, welcome to this clip having a look at manganate titration questions. We're going to have a quick look at how the manganate titration technique works, and we're also going to look at something called data moles equation moles answer. This is a way of processing the data and turning it into moles using the equation and then getting the final moles and getting the answer. So it's a way of sort of dealing with large quantities of data coming at you to work out moles at the end, so you don't get confused during a twist. So the purpose of this is to use the titration to find the moles of iron in a solid sample. The sample might be impure, for example. So if we have a look at the question, we've got 200 grams of an impure solution, which is added to a beaker and dissolved in 250 centimeters cubed of sulfuric acid. 25 centimeters cubed of that solution is added to a flask and titrated against 2 moles per decimeter cubed of potassium manganate. There's quite a lot of stuff being described there in only a few sentences. So let's just take a moment to kind of visualize what it means. You start with 200 grams of an impure Fe2 plus in the form of a typical iron 2 salt, maybe FeSO4, for example. The wording of the question where it says impure suggests that not all of that 200 grams is your iron sulfate, for example. There might be other things in there as well. So we need to find out really how much actual iron is there, and we're not interested in the impurities. So we know that iron reacts with manganate, so we're going to try and isolate the iron if we can. So the first thing to do is to dissolve the solid in some sulfuric acid. The reason for the sulfuric acid and not water will become apparent in a moment. Then you take a small portion of that, 25 centimeters cubed to be exact, and you put it into a conical flask. So that's chosen because it's a nice easy scaling factor. It's a tenth of the amount we started with. But not all questions will give you this in that particular easy form. You might have to do a bit of calculating to work out how many times this goes into this, for example. But I'll show you how to do that in a second. So you add your standard solution of potassium manganate, and now we're ready to go. So our first piece of processing is to write out the redox equation. So in a nutshell, how this works is the manganate has 4 oxygens, which require 4 waters for the oxygens to end up in. So you're turning manganate into just a manganese 2 plus, so those oxygens have to be given somewhere to go. They end up in water, and to do that you need 8 hydrogen atoms. 8 hydrogen atoms comes from 8H+. 8H+ will come from the dilute sulfuric acid. So if you do the oxidation numbers, the manganese in manganate is +7, and it's reduced back down to +2. That means a gain of 5 electrons. Whoops. So just repeating that. Going from +7 to +2 means you gain 5 electrons. Now those 5 electrons have to come from somewhere. So that somewhere is your iron. Now your iron starts as 2 plus, ends up as 3 plus. That's only a loss of 1 electron. So you have to have 5 irons, each giving away 1 electron, to provide the electrons that the Mn needs to turn it to Mn2 plus. So from +7 to +5. Okay, let's have a look. Working out the titers gives us these values, and we have to decide what's concordant when we're using the average titer. Don't use 3 titers, 1, 2, and 3, for example. You have to decide which 2 are closest to each other within 0.1 centimeters cubed. So I'm going to go for the 2 red ones I've highlighted there. That's a piece of processing which gets some credit. Now we can get the page laid out for our calculation a bit later. So we work out the average titer. We get 26.475. This is a calculator value now. It's not a reading like these two. So these two have to be quoted in to the nearest 0.05 centimeters cubed, because that's the accuracy to which the burette works. This is not coming from the burette directly. This is coming from an average of the 2 closest ones. So therefore, this can be quoted in the full calculator value. So the information that we have for manganate allows us to work out the number of moles. So we put that information down, and that allows us to work out 0.05295. So the equation, as you can remember, and as you can see at the top, tells us that the moles of manganate to the moles of iron 2 plus is 1 to 5. So all you have to do is multiply the moles of manganate by 5 to get the quantity of Fe2 plus in moles, which is now 0.26475 moles. So the scaling factor I referred to earlier is this. So this is your original solution. This is the small proportion of it that you titrated. The titrated part is what you know the moles for. So how many times does this go into this basically? So you divide 250 by 25 to get 10. So obviously this value here, 2.6475 moles, is in the original 250 centimeters cubed of solution. If you remember right back to the very start, that's what the solid was dissolved in. And we're interested in how much iron is in that sample. So that's where you get credit in terms of marking points, because each one of those things that we did at those places is actually a new piece of processing. So now we need to take that piece of information we've just worked out to work out the percentage purity in solid. So that's the key piece of information from the DMEMA calculation. So we want the mass in that amount, the mass of iron 2+, because that's going to be the same as the mass of iron. So iron 2+ and iron are obviously very similar. One is an ion, one is an atom. So going to our periodic table, you can see that iron has a molar mass of 55.8. So we multiply our 2.6475 times 55.8, and that gives us 147.7305 grams. So the percentage of purity is dividing that by 200, remember the original 200, and then multiplying that by 100 to get this value. But they wanted to 3 sig figs, so I'm just going to turn it into 73.9%. So here's a quick look at the whole process from start to finish with a few justifications and annotations. I hope this has been a useful look at how a redox titration and an associated calculation might work. As always, thanks for listening, and until next time, see you soon.